When last we met, I established the electric field due to a point particle. Here I have, by way of review, the electric field, certainly a vector, some constants of proportionality, 1 over 4 pi epsilon naught, the charge that creates the field, which I'm, to this point, imagining is a point particle in space. It has no physical dimension. It is the source, in the case of positive charges, of the sink, in the case of negative charges, of electric field. With the 1 over r squared dependence that makes our electric field similar to the field of gravity, and an r hat tacked onto the end of it so that I know that it's a vector quantity that I'm describing. A couple of properties we investigated with that is generally the nature of the electric field, that it points away from positive charges and toward negative charges, that a positive charge placed in an electric field experiences a force in the direction of the field. And then a negative charge feels a force in the opposite direction. So if I limit my understanding of the electrical phenomenon to just that, the interactions of charged particles, I'll find that the science is quite lacking, because unlike the nature of gravitational interactions, where very often we're considering individual objects and their sort of particle nature, not particle as in lacking physical extent, but particle nature in the sense of being mechanical parts of a system, like the motion of the planets around the sun. In contrast to that, the electrical phenomenon are often investigated or manifest in the nature of the world in the context of many particles, an uncountable number of particles. So many charged particles that they can be viewed as a continuum in space. And so while it's excellent that I have this definition of electric field, and we'll find that there's great utility in it, it's not very practical unless I'm considering the motions or interactions of individual subatomic charged particles. So what I'm going to do today is imagine if I can devise some technique, and indeed it's true, that I can calculate the electric field due to distributions of charge in space. And so I just want to, before I get into doing it, what's going to happen is I'm going to give several examples, and in a certain way these examples build one upon the other. But before I get into the practical examples, I want to give you an idea of the general technique that will be applied, which is the same in the context of every example. Imagine, for the most general description here, that I have a distribution of charge in space. What I'm going to draw here is just sort of a irregularly shaped object, and I would like, and it has some charge. I'll give it a charge plus Q here, so I'll just indicate with a large capital Q. This is a fixed amount of charge that this object has. Is it distributed, or how is it distributed in space? Is it uniform? It can have any kind of dependence that you can imagine. Perhaps there's more charge down one end than there is at the other end. Perhaps the charge, there's less charge in the interior of this, what presumably is a three-dimensional distribution of charge in space, and more charge at the surface. However you can imagine charge arbitrarily distributed through space. And what I would like to know is that if this charge exists here, what then would be the electric field at this point in space that I'll call P and draw right there? Well, clearly I have a problem. I cannot calculate the electric field at this point in space by treating my distribution of charge as a point particle. That, I think, is rather obvious, but let's get specific about the reason. When I calculate the electric field according to this relationship, I must know the charge Q, which is fine. I imply that I know how much charge I've gathered here in this region of space, but also I have to be very specific about what is R. R is the position vector from the charge to the point of observation of the field. Well, because of this charge distribution takes up a region of space, it's no longer clear what R should be. If I select some of the charge that's here near the top of the distribution, it's quite close to the point P, and the vector points, I guess, somewhat downward. And then if I look over here, I find that the charge is much greater distance, a larger R from the point P. And so it becomes sort of ambiguous how I should calculate. Well, there's a relatively straightforward way to proceed that should be somewhat familiar to us. Imagine that instead of considering the entire distribution of charge, I consider only this small part of it. A little unction of charge here down in this low region. I chose that quite arbitrarily. It's very, very small part of the charge. In fact, I'll say that it's an infinitesimal bit of charge right there, and I'll label it dq. It is a differential of charge, infinitesimally small. Well, that infinitesimalness of that charge makes it, I was going to say a good approximation of a point particle, but in fact it makes it a point particle because it has no physical dimension in space and it has a very specific amount of charge. And if I draw a vector r from my differential of charge dq to the point of observation of the field in space, and I call that the position vector r that I use to calculate the magnitude of an electric field, then this differential of charge dq will create at the point P a differential of electric field, which I'll wisely name dE. And so there it is. A really important thing just happened that's subtle. I drew the differential electric field vector away and in the direction of the radius. Electric field points in the direction of r hat in this definition. So it should definitely be parallel to the radius vector that I've drawn. And I've drawn it radially away because I know that we've decided by convention that positively charged particles, which I've implied that this entire distribution has a positive charge, but positively charged particles produce electric field that is radially away. Here's the important point. I was able to determine the direction of the electric field in this context by reason alone. I didn't have to do any sort of mathematical machinations or find the components and then do some inverse tangent to find the direction. I didn't have to do any of that because I have some appreciation of the regular natural behavior of electric field in the vicinity of charges. And that's going to be the reason why I emphasize this now is going forward. I'm going to say it many more times, that the direction of the electric field is often determined by reason. And it's the magnitude of the electric field that I seek to find. And so what I have here is a contribution of electric field in space dE, which is a differential contribution produced by dq. But of course, if I wanted to know the entire electric field, I would have to add up all of the contributions. That is going to be a vector sum. Even though I've reasoned out the direction of the differential of electric field, another differential of electric field that I choose based on different dq positioned somewhere else in the distribution is going to be in a different direction, and they do not add as scalars. They add, according to the principle of superposition, as vectors. And so it'll be a vector sum. What I'm implying is this. If I have a distribution of charge in space, like this one I'm used by way of example, that the total electric field will be the integral, the sum of the differential electric fields. You may think right in this moment that this doesn't get me any closer to finding out what the total electric field is at point P, because now I have to ask the question, well, what is dE? If I'm going to add up all these differentials of electric field, what shall I substitute in for dE? Well, I've already given the hint there. I'm dividing my distribution of charge up into individual differentials of charge. They are my point particles, and they create a very well-defined differential of electric field. Consider again that the electric field is 1 over 4 pi epsilon naught q over r squared r hat. All I'm going to do is replace the capital Q, that is the electric field created by a point charge capital Q, and replace the Q with dq. It goes like this. I'll write the constants outside of the integral because we're in the habit of doing that. 1 over 4 pi epsilon naught outside of the integral of dq over r squared. And I'll leave off the r hat because in a sense I'll do the magnitude. I wrote harpoons on here, perhaps they don't belong. So that the magnitude of the electric field will be the integral of, well, leaving off the harpoons, I have to have the harpoons because it is in fact a vector quantity, and this is in fact a vector sum. So I'm going to go through and be a little bit more careful with my notation, which I should be doing anyway. Shame on me for even considering it. So now I have to perform this integral. Well, in the example that I've done here, performing the integral is going to be extraordinarily difficult to do because of the irregular shape of the distribution of the charge in space. It is unlikely that I'm going to solve this integral, and if I could solve this integral, it would not be trivial to do so. What I'm interested in doing today, sort of the theme of today, is evaluating this integral in a few specific examples where the calculus is interesting, perhaps even entertaining, but not beyond our ability. We're not going to let things get too out of hand, but we will stretch our legs with some calculus and investigate the electric field created by some distributions of charge in space. The first example that I would like to do is the rod of charge. So I'll just write here that we're going to do a rod of charge. What I mean specifically is I'm going to take some charge plus Q, and I'm going to form it into a rod here, which presumably has a length capital L. So here I have a rod that I've arranged on an x-axis that doesn't exist yet, but there it is, sort of arranged horizontally. A rod that has a total charge plus Q, so I'll mark that there, plus capital Q, has a total overall length L, and I would like to find the electric field due to this charged rod. Well, where are you looking? Because whenever I'm interested in investigating the electric field, I have to say where in space would I like to know. Now you might jump the gun a little bit and say, well, Shadley, I want to know what is the electric field everywhere in the vicinity of the rod, above, below, in front of, to the left, to the right, that's somewhere in between. Well, it turns out that choosing the location where I would like to evaluate the electric field has a tremendous effect on the difficulty of the problem. It turns out to be completely doable, but not so simple to find the electric field at an arbitrary location in space. So to ease our way, I'm going to be very specific and say that off to the right of my rod of charge here, say at this location in space, which is a distance a from the end of the rod, that is where I would like to know the direction of the electric field. That'll be good for an initial exercise to sort of try this out and see how it feels. So I have this charged rod here, and I'd like to know the electric field at that position. Well, the first thing that I'm going to do is appreciate the fact that I cannot treat a rod of charge as a point particle. Because of course I have here the right end of the rod, which is very close to the point of observation of the field, and I have the other end of the rod, which is far from it. So there's no clear position here, or distance, no clear radius that I can use. I should say radius, should say position vector that I can use to describe this. And so what I'm going to do is divide the charge distribution up into differentials of charge. In calculus, we do this as sort of a mathematical strategy to compose an integral that can be solved. Many of you remember doing volume integrals and solids of revolution integrals and so on. It's a similar process, but here it has some physical meaning. Imagine if I divide this rod up, and here at an arbitrary location, I'm going to say there's a certain length of the rod dx. And that dx contains a certain differential of charge dq. Now, the r vector, the position vector that points from my differential of charge to the point of evaluation of the field, is very precisely defined. That dq is a point charge. All I need to do is carefully write an expression for the differential of electric field that's created by that charge, and then integrate that over some sensible limits in order to get the total electric field. Here's how we proceed. The first thing that I would like to do, and I think I may have already said first thing first. Well, we'll see. A thing that's important to do at this step or this stage of it is to imagine what the electric field sort of looks like. That exercise in the last lecture of imagining what the electric fields look like in the vicinity of charges was an important one. Because very often when I solve problems of this type, I need to have a little visual idea to inform how I proceed. The rod is positively charged, which means it's a source of electric field. And by the symmetry of the thing, I imagine here at my point off to the right that the differential of electric field will point along the x-axis to the right. So I'm going to write dE here. And no matter which dq I choose, imagine I slide back and forth on the rod here and choose different dqs, the differential of electric field is always directed to the right. So once again, I have reasoned out the direction of the field without doing any kind of calculation to get it. And so what I need to find now is the magnitude of the electric field in order to satisfy this. So I need a coordinate system in which to solve the problem. And since the nature of the physics of the thing is completely independent of coordinate system, I can choose the coordinate system however I like. There's an interesting trade-off that happens here in the calculus that some of you who are very interested in the mathematics of these things might find of some interest, and that is, I have many different ways that I can choose my system of coordinates. Some are wiser than others, and that's no surprise. But it turns out here in particular that I really have two choices ahead of me. One is to choose my choice of coordinates so that the integral is easy, but the limits of integration are complicated. Or choose my coordinate system so that the integration is a little bit more complicated, but the limits of integration are very simple. I choose the latter. I'm going to go for simple limits of integration. You might choose as an exercise later on to give it a try the other way around and see that you get the very same result. Here's how I choose my coordinates. My choice of coordinates. I've been harping on that the whole time we've been talking about physics. The choice of coordinates is always mine. I'm going to choose the origin of my coordinate system here to be the right end of the rod. And in a surprising plot twist, I'm going to choose to the left to be the positive direction. I'll indicate that here on my diagram in my customary way. So I've chosen the origin of my coordinate system to be at the right end and to the left to be the positive direction. The reason why I've done this is that as I evaluate the contribution of each dq at the point of interest here off to the right where my differential of electric field is, the limits on my integration will be from 0 to L. As I evaluate the integral from right to left, that gives me simple limits of integration. We could have an argument about this. It's a style thing. Why do I want simple limits of integration? Well, in the end, when I evaluate the limits, I would like there to be very little algebra, because by the time I get to the end, I'm going to want to simply wrap the thing up as quickly as I can. So now, to find the electric field, that's going to be our task. So what I'm going to do is solve this new integral that I have. The claim that the total electric field, which I don't need to write as a vector here because I've established the vector direction, is 1 over 4 pi epsilon naught, my constants that just sort of sit out front here. I could be writing K, Coulomb's constant here, but I find that the integrals, I find it aesthetically pleasing to carry around 1 over 4 pi epsilon naught. And just a few discussions from now, we're going to realize that there's meaning inside of that we're going to investigate. It'll be of interest, and we'll be able to write some solutions in a simpler way in that context. So there's my constants, the integral of dq over r squared. Now this is a little bit familiar from integrals that we solved in our study of mechanics. We find ourselves in this situation where we look at the integral and say, well, I can't solve that, so I need to do something that's going to make the differential, in this case dq, commensurate, or commensurate? I guess commensurate's an okay word. Like, I have to make the differential dq agree with the variable r. And right now they're not in agreement, so I have to find some relationship between the two. This will be familiar from center of mass and moment of inertia calculations. What I'm going to do is bring back my old friend lambda, the linear density. But in this case, lambda is not going to be a linear mass density, as I did, for example, when I investigated the center of mass of a rod of mass. Here, it's going to be a linear charge density. I'll take the total charge of the rod, which I've presumed is plus q, and divide by the total length of the rod. So q over L is the linear mass density. Here, I'm making an assumption that the charge of the rod is linearly distributed. It's uniform, not linearly distributed. That's not what I meant. Pardon me. I'm making an assumption that the charge on the rod is uniformly distributed. This relationship here, lambda is q over L, could very easily be a function of x. All that would do is complicate the integral. There wouldn't be any extra physics in that. It would simply add more variables in the integral in amusing ways that would make the integral more challenging to solve. So we'll leave that sort of thing for the exam. And here I'll make it easy for me and for us, because it's an introduction to the thing, by choosing to make the charge uniformly distributed. So it's q over L. Well, it's a relationship among the differentials that draws my interest. And so what I'll say is that if the density is q over L, then that density is also dq over dl, a differential of the length. But since I have oriented this charged rod along the x-axis, that dl is of course dx. And what I have here quite simply is the relationship that I need between dq and the spatial variable, which is dq is equal to lambda times dx. That's very satisfying, but it's not sufficient, because the variable that appears inside of my integral is not x, but r. So what do I mean when I state that variable r? Well, the variable r, and my diagram is now too crowded to add it in, so we're just going to have to visualize, please, that the r vector is the vector that points from the charge, which is my dq here, to the point of observation of the field. That value is complicated, well, a little bit complicated, because I don't have any geometry or values in my problem that make it immediately clear, like I haven't named it yet. R, I guess I'll draw it here on the diagram. I'll give it a try and see how it feels. R is this distance from dq to the point of observation of the field. Well, that's made of two parts. The position x of the differential of charge dq in this coordinate system, so there's x right there, plus the distance from the right edge end of the rod to the point of observation of the field. That is, in this coordinate system that I've chosen, r is equal to x plus a. So I have two substitutions to make here. I'm going to replace dq with lambda dx, and I'm going to replace r with x plus a. And I'm on my way to creating an integral that I can solve. I think, respecting the fact that lambda is a constant and that we've been at this game of physics for quite a while, you won't mind at all if I bring the lambda outside of the integral and simply write dx over x plus a quantity squared, because the r is squared in that. Now all of a sudden I find myself within it. Now I feel like I'm in calculus class now. It just took me a bit to focus on the setup of the problem in order to create an integral that I can solve. Now, we're mostly new to the field of calculus, so maybe we gulp for a second at the integral. Don't worry, it is quite trivial to solve, and we'll solve in just a moment. Let's consider, before we do though, the limits of integration, which I've pointed out, I've deliberately selected in such a way to make them simple. They go from 0 to L. Will be the limits of integration. So now it becomes an issue of calculus to solve the integral. I'm going to solve it with a bit of overkill, because to me this integral is quite simple. I'll do it immediately without any trouble. What am I going to do about that x plus a? Well, the x plus a doesn't bother me at all, but it may bother some of you. So I'm going to proceed very cautiously and with an abundance of too much caution. I'm going to use a u substitution in order to evaluate this integral. And my choice of u is fairly obvious. The thing that bothers me about it is the x plus a that appears inside the square in the denominator. So making my u substitution, I'm going to say let u be equal to the quantity x plus a, and then I immediately take the derivative du dx, which is equal to 1. And therefore, the differential du is equal to the differential dx, and that's why this integral doesn't bother me. The u substitution doesn't really change anything. The u substitution, in a sense, teaches me that this integral, that the x having an a added to it, the x plus a, doesn't really change the calculus of it. Here's what I mean. Making the substitution of the u into the integral, I'm going to leave my constants out in front. Here's my lambda and my 4 pi epsilon naught. The integral, I'm leaving off the limits because I'm doing a u substitution. The limits will return momentarily. This is going to be du, because dx is replaced with du, divided by u squared, which of course is a trivial integral to solve. The integral of 1 over u squared is negative 1 over u. The integral of u squared is negative 1 over u. And so I'll write this as lambda over 4 pi epsilon naught. I'll just write it in, being as complete as possible. I suppose I'm in a mood today to sort of move things along rather swiftly because I feel comfortable with what I'm doing. But I'll try to make every step as we go. Well, this is in terms of u, which is not the variable of my problem. So what I should very much do is replace the u with what I know u to be equal to. And so I'll put lambda over 4 pi epsilon naught. Some of you may be wishing that I had left the k in, because then there would be a whole lot less of writing of those constants ahead. But I have sort of a romantic notion that I have, and so you're not going to be able to disabuse me of it. X plus a, and now returning my limits. My limits of integration were 0 to L, and so I have an easier time now, I think, in evaluating these limits. Once again, final minus initial, here I go. The electric field would be equal to lambda over 4 pi epsilon naught. There we go. Now the evaluation of the limits. Starting at L, it's going to be negative 1 over the quantity L plus A minus the negative quantity, and so plus 1 over 0 plus A, so 1 over A. I'll want to combine these fractions and do also, I'll probably want to reverse the order of the fractions. So I'm going to reverse the order and add the fractions simultaneously. I don't want to bore you necessarily with simple feats of algebra. So adding the fractions, my denominator obviously is going to be A times the quantity L plus A. So A times the quantity L plus A, and over here I'm going to have an L plus A in the numerator, and then minus A over A times the quantity L plus A, and that's those two fractions with the common denominator, and when I subtract, I'll have an A in the numerator, subtracting away an A, and I'm going to end up with an electric field that is equal to the linear charge density lambda over 4 pi epsilon naught times the quantity L over A times L plus A, just like that. Now, in solving the integral, I sort of contrived the linear charge density lambda. I invented that in order to make that relationship between the differential of charge and the differential of position. Sometimes when I'm asked to solve these problems, homework, exams, those kinds of situations, sometimes it's considered very acceptable to leave a charge density in the problem. In fact, sometimes the charge density might be unknown, and so it needs to be in the problem. But here I know what my charge density is. It's a uniform density, which is conveniently the charge per unit length. The reason why I say conveniently is when I replace lambda with the charge per unit length, the L's are going to cancel. And so what I'll end up with here is an electric field that is equal to Q over 4 pi epsilon naught multiplied by L over A times the quantity L plus A. Now that, for our first example of integrating a charge distribution in order to determine the magnitude of the electric field at a particular point in space, that was fairly straightforward. All of its parts. It's a very essential exercise. Later on, you should attempt to redo it. Take a blank paper and see if you can formulate these arguments. Not because this problem itself is particularly important. It is a useful result. But more importantly, because the techniques used in this solution are going to happen over and over and over and over again. And I'm looking forward to demonstrating them again and again so that we can begin to see these patterns. So it's not terribly complicated, but at the end, I'm saying that the electric field is Q over 4 pi epsilon naught L over A times the quantity L plus A. And you might say, well, okay, if you say so, I don't have any way of knowing. Does that seem right? Well, there's a couple of ways that we can look at our answers and not simply say, well, I guess so, I did a bunch of math, hopefully it's correct, but actually evaluate them in the context of the physics of the thing. Our electric field of point particles is proportional to the charge. The magnitude of the field is proportional to the charge. And here I have an answer where the magnitude of the field is in fact proportional to the charge. There it is, right up front, capital Q, proportional to the charge. That's not really that surprising. You might have guessed that that was going to happen. The appearance of 4 pi epsilon naught is no surprise at all because it was hanging out the entire time. It's the quantity in brackets here, L over A times L plus A, that's the struggle. Often, a way that I can evaluate my results to determine if they're correct, beyond dimensional analysis, beyond the presence of constants, is to evaluate the expression in the extremum. And here in particular, what happens if the point that I choose to observe the rod is very far from the rod? Instead of being very close here at a distance A, which I've drawn it just the way that I drew it, where A was less than the length of the rod overall. What if I made A very large indeed? Well, look how this behaves. Imagine here in the denominator where I have my quantity A times the quantity L plus A. If I distribute the A, that's A times L plus A squared. When A becomes very large, that is, if I examine the value of the electric field at points very far from the right end of the rod, when A becomes very large, it's A squared in the denominator. The A squared term dominates, and this function for electric field becomes Q over 4 pi epsilon naught 1 over A squared. The 1 over a squared dependence dominates. And the reason for that is that if I'm very, very, very far away from the rod, a large distance from the rod compared to the length of the rod appears as a point particle. At some point, I'm so far away from the rod that the point particle solution is a good approximation of the electric field. And so that's a way of evaluating this result that I've obtained here in terms of, did I get the right answer to the thing? My next example has some different features, although the principle is the same. What I'd like to do is imagine that I have a rod of uniform charge density, just as in my first example, except this time my rod is going to be curved into a semicircular arc like this. This arc subtends a particular angle. So what I'm going to do is I'm going to draw in my x-axis here, and I'm going to suggest that there's a certain total angle theta that goes along here. And I'm looking for the electric field at a particular location in space. Just like in the last example, you might say, well, let's find the electric field everywhere. Well, it would turn out to be a significant challenge. So taking advantage of the geometry of the thing, I'm going to ask a contrived question. What is the electric field at this point, which is at the center of curvature of my rod, or my curved rod, my arc, of radius r, and I'm going to call that radius capital R there, for reasons that will become apparent as we go. I want to find the electric field at that location in space particularly because, if I'm being completely honest, there's a certain ease to the determination of this integral. So I'm going to follow my procedure and say that in order to appreciate the electric field at this point, I'm going to divide my arc of charge into some differential elements, dq here, and consider each differential element as a point particle that creates an electric field here at the point of observation of the field, the center of curvature, dE, which I'll draw. You see, it's off here at an angle here, and I put a harpoon on it because the vectorness of this contribution to the field is of interest in this particular solution. Now, I know what the formulation, what the strategy is. I'm going to go along and add up all of the contributions, but I have to add them as vectors. In the previous example of the rod, it wasn't a concern because all of the differentiated or differential electric field vectors pointed in the same direction along the x-axis. So their vector addition was very much like scalar addition, because I simply had to add the magnitudes as I went. Well, now, if I consider another dq located elsewhere on the arc, there'll be a differential of electric field contribution that is not in the same direction as the dE that I've drawn here. So a little bit of thought is required. An interesting symmetry that you may spot here is that if I consider this dq here at the top of the arc, as I've already done, it has a symmetrically replaced dq near the bottom of the arc, and I'll draw that in here. Here's a dq that produces a, in some sense, symmetric dE this way. That is, the differentials of electric field don't point in the same direction, but their angle with respect to the x-axis is the same. The interest comes when I evaluate the components. See here, this differential of electric field that is above the x-axis has two components. A y component of the electric field, which I'm content to call EY, I should call DEY actually, and a component of the electric field directed along the x-axis, which I'll call DEX, the x component of the differential of electric field. Well, if I consider my electric field differential contribution below the x-axis, it has similar components. Here, a y-axis component of that electric field directed downward, which I'll also call DEY. Because both electric field contributions are at the same angle with respect to the x-axis, these vertical components cancel. And because every dq that I choose above the x-axis has in some sense a mirror reflection below the x-axis, then these y components will always cancel. So as a result of this reasoning, I understand that the electric field that I'm looking for is not going to be found by adding up the differential of electric field contributions, but instead by adding up only their x components. So what I mean here by this is that the total electric field I seek to evaluate is the integral not of dE, but of dE x, the x component of the dE's. Well, how am I going to compute that? Well, I need to know what the angle is so that I can write the component. Imagine here my original dq above the x-axis that I drew. I'll draw a dotted line out there to indicate that radius and show the angle theta between the position along the arc of that differential of charge dq and the x-axis. I'll call that theta. Well, that means that the angle of the differential of electric field contribution is also theta, and therefore the dEx component that I'm seeking to integrate is dE multiplied by the cosine of theta. And I know from the reasoning of the thing that when I find the total electric field, it will be directed entirely along the x-axis. So once again, I want to emphasize that I'm going to find the magnitude of the electric field through a process of integration, but I'm finding the direction of the electric field according to some careful reasoning. And in this case, it indicates once again that the electric field will be directed entirely along the x-axis. So now I have to perform this integral, so let's get to it and see what we have. So we construct this integral into something that we can solve. Well, there's my differential electric field that appears. So I'm going to write this with the constants out in front because that's always going to happen anyway. So I'll write 4 pi epsilon naught, the integral of dE, which is dq over r squared. That's certain. But now also multiplied by the cosine of theta, so I'm evaluating the component of the magnitude of that electric field. Well, now all I have to do, same as I did, see, I want to be clear that there are similarities in the procedure. Each one of the examples that I might do, or that I study, or that I find on a test, they all have their own quirks and specific context. But there are commonalities in the problem solving. I need to take this integral and formulate it into something that I can an integration that I can actually perform. Well, there are a couple things of interest here. First of all, I'll address the fact that the r squared that appears in the denominator here, dq over r squared, that r is the distance from every dq to the point of observation of the electric field, which is the center of the arc's curvature. Therefore, that lowercase r squared is actually capital R squared, the radius of the arc, and therefore a constant. It can be drawn from the integral. So my electric field is then 1 over 4 pi epsilon naught capital R squared, the integral of dq times the cosine of theta. Well, now I need a relationship between dq and theta. Well, my differentials of charge, dq, exist in little segments of arc length. When I say arc length, I specifically mean the arc length. According to the arc length formula that we're all familiar with, S is equal to R times theta. I used a lowercase r there, but probably capital R. Pardon me. This is the relationship between arc length and arc angle, or the angle, the arc angle, that's fine, the number of radians. And so the differential relationship is simply ds is equal to the constant r d theta, is the relationship among the differentials. So what I'm going to do with this relationship between d theta and ds is once again do my trick with the linear density. Even though the rod is bent into the shape of a semicircular arc, it still has a certain amount of charge per unit length. And if I knew the total charge of the arc, which in principle I do, divided by the total length of the arc, which is a little bit more ambiguous, because the total length of the arc, of course, depends on the total angle subtended, which I did not indicate in my diagram. So it's sort of like, I know that there's a charge per unit length, but I don't explicitly know, because I haven't exactly said what the total arc angle is. And you'll see, as I get to the end of the solution, why I've made that choice, which is a choice of style and not necessarily a choice of physics, but we'll discuss at the end. So if this is true, for the charge per unit length, being lambda, then it's true for the differential charge per differential length, which in this case is a differential of arc length. Now, if I go ahead with this, it's going to relate dq to the differential arc length. And I need the relationship to the angle because I've got that cosine in my integral. And I need the variable, which is the angle. Imagine that I'm evaluating this integral and I look at all of the dq's. They all have a different angle. Theta is the variable of this integration. Well, what I'll do is use this very convincing relationship here, that ds is equal to r d theta, and appreciate that the r is the capital R. And so dq, that is the radius of the arc of charge, is going to be r d theta, and that of course is equal to lambda. And so now I have my relationship to replace dq. I simply have to stir it around a little bit so that dq is equal to lambda times r times d theta. So I'll make that replacement in my integral, and once again I'll just pop the constants out in front, and I'm going to leave the r's alone and not cancel them immediately. I know that sometimes stylistically I may frustrate some of you with the things that I choose to do, but I'm just making all this up anyway. So lambda times r over 4 pi epsilon naught capital R squared, where obviously I'm going to make an effort to cancel those r's. The integral, and now I find, as is so often the case, that the challenge of these things is in fact setting up the integral, getting it to a place where you can say, well, I can integrate that. And the integral itself turns out to be a fairly trivial one. We all know, I think, some people have already jumped the gun in their minds. They know what the integral of cosine is, but that in a moment. Because first I should consider, what should be my limits of integration? Well, there's a little bit of a clever trick here that I'd like to use to appreciate the fact that there's symmetry above and below the x-axis, and to avoid trying to remember what the sine of negative theta is. You'll see in a moment. I'm going to do the following. I'm going to appreciate that if I were to integrate theta as it goes from 0 to theta, I would get the contribution of half of the arc. But because of the symmetry, if I were to integrate down again, I would get the other half of the arc. So what I'm going to do is put a factor of 2 in front of my integral, and along the way I'll cancel these r's. So I'll have 2 times lambda divided by 4 pi epsilon naught r, the integral from 0 to theta of the cosine of theta d theta. And so I'm doing the half integral and doubling it, taking advantage of the symmetry. And I wanted to do that here particularly because it's a strategy that happens in more advanced physics, in our problem solving. It sometimes helps me get around little quirks of calculus or things that happen. It can be a useful tool, but it's not so commonly used that it's necessarily on hand. So I had the opportunity to include that in my demonstration, and so I did. So now my total electric field is coming down to me knowing that the integral of cosine theta is in fact the sine of theta. So what I'll do is write 2 lambda over 4 pi epsilon naught r. The sine of theta evaluated from 0 to theta. Well, the sine at 0 is 0, and that's a convenience. And so what I get here is my final result for the electric field. At the center of an arc of charge, reiterating again that I have not found the electric field everywhere, but an electric field at a particular point in space. And again, if you feel that that's not sufficiently ambitious, try to find the electric field at other points in space. You're welcome to do that. You may find that that offers a significant challenge. But the number one lesson here, the importance of doing this, is to compare this to the previous result and compare it to all future results and understand and appreciate the commonalities between these problems, because recognizing those things is going to make it possible for us to be more successful in problem solving in general. It's somewhat a curious thing, I think, that my very next example, you can make an argument that it's the simplest of the examples that I'm investigating today. I want to find the electric field in the vicinity of a charge, positive Q again, that is formed into a ring. Now this diagram I'm about to create is a 3-dimensional diagram. It's a bit tricky, and as you see right off the bat, it goes wrong for me and I have to scrub it out and start again. There we go. Now this is a ring of charge. I want you to be careful. It is a circular ring of charge. And as we're viewing it here, we're seeing it sort of three-dimensionally. So that we can tell that it's a ring, we've leaned over slightly, turned our head a bit, so that we can see it sort of in a three-dimensional sense here. So this is a ring that has some radius. I'm going to do a bit of funny business here that you'll be curious about. But as it happens, this solution I'm going to carry over into the next solution. So I have some requirements that won't become apparent to you until later on in the argument. Here's the x-axis, and I've tried to draw it. I haven't done very well, so once again I go trying to improve my diagram. Draw the x-axis through the center of this ring, and I'll say that the ring has a total charge Q, as I mentioned, positive charge again. It has a radius A, and it creates electric field everywhere in its vicinity. But once again, I'm going to ask that we endeavor to find the electric field at a particular location along the x-axis, somewhere out here, a distance x from the center of the charge distribution. So this is the point at which I'd like to observe the field. Now that x, once I've finished my solution, I have my answer, I can still treat that value of x as variable and move it along the x-axis and imagine what the electric field should look like. And when we get our answer, we'll do some investigation of that. But here I want to find the electric field there. You know the drill. I'm going to take my distribution. We're going to become old hat at this just in an hour or so of discussion. But I'm going to take my charge distribution plus Q and divide it into differentials of charge dq, each of which presents, I'm going to have to do a little bit of diagramming here, each of which creates a differential of electric field that appears here at that point. And hopefully, if you're paying careful attention, you'll say immediately, well, I see what's going to happen. That this dq that I drew at the very top of the circle provides that component or that contribution, dE, at the point of observation. But you know there's another one symmetric right at the bottom of the thing. And that symmetric contribution goes like this. So once again, it seems as though the y components of this are going to cancel. And indeed, it's true. Once again, in order to find the total electric field, I'm going to be integrating not the differential of electric field, but the cosine component of that differential of electric field. Here's a little geometry. In order to establish the angle sort of geometrically in my diagram, I'll draw this dotted line down from my top dq to the point of observation of the field, and appreciate that the angle of the electric field with respect to the x-axis is, what do you say, not alternate interior, that's a different rule. There's a rule for that. Common vertex, maybe, I don't know, they give these things names. But if that angle there is theta, then the angle of the differential electric field vector is also theta, and its component, therefore, is dE cosine theta. Notice, however, that in this problem, the theta that was a variable in the previous example is now no longer variable. Remember, this distribution is circular. So if I were to imagine examining all of the dq's, a kind of animation in my mind, if I were to investigate all of those dq's, this dotted line that I've drawn on my diagram would form sort of a cone. The angle is constant. The angle theta in this problem is not a variable, but is instead constant. And we're going to discover that this is going to create a very, very simple solution to this integral. Here I go. We're getting some skill, so I feel like I can move ahead and say that the total electric field is going to be the integral of the differential of electric field times the cosine of the angle. It's these components. So I'll drop in my standard differential of electric, well, once again, if I'm following the pattern that I've been doing, I'll draw the constants out in front, 1 over 4 pi epsilon naught, the constant in front, the integral of the differential of charge dq divided by r squared, which requires some explaining, multiplied by the cosine of theta. Well, now investigate. Every differential of charge dq is equidistant from the point of observation. Sure, I've got charges at the top, at the bottom, and the left, and the right all around the ring, but every one of them is the same distance. Appreciate looking at the right triangle of my diagram here, that the distance between this dq at the top of the diagram, which I've showed, and the point of observation of the field is the square root of x squared plus a squared, a little Pythagorean theorem there. And so if that's that hypotenuse of that triangle, then the r squared that appears in the denominator of this integral, that r squared, is just x squared plus a squared, which for a particular choice of x is a constant and comes out of the integral. And the cosine of theta is a constant and comes out of the integral. So I'll write this as the electric field, just sort of going along in individual steps here. I guess I'll write it as cosine theta divided by 4 pi epsilon naught 1 over, oh, I'm writing this in an ugly way, x squared plus a squared, the integral of dq. I'm not entirely pleased about how I wrote, what I'd rather do? I'd rather have the 1 over the 4 pi epsilon naught and the cosine theta over the x squared plus a squared like that. It's all aesthetics, and perhaps you would have written it differently. Now here's a curious thing. I'm left with integrating only dq. Everything else is constant. I don't have to do anything here to say that dq is related to ds at an angle and integrate all the way around. I could do that exercise, but at the end of it I would feel a little bit hollow and upset because I would have realized my own absurdity. The integral of dq means add up all of the differential of charge, or differentials of charge. If I do that, I simply get q. So my result for the electric field is q over 4 pi epsilon, well, not my result because I have further steps to do, but q over 4 pi epsilon naught, the cosine of theta, divided by x squared plus a squared. This is bad form. It's bad form because I have the variable x in my answer and I have the angle theta. Notice that they depend one upon the other. If I were to, again, in my mind, animate my diagram and move the position of the observation of the electric field, I would find that the angle theta would also change as x changes. So there's a relationship between them. I could endeavor to write this expression purely as a function of theta, and that would be fine. But I've said I'm interested in it as a function of x, and so that's what I'm going to go for. So I need a way to express cosine theta in terms of the geometry of my diagram here. Well, I know that the cosine of theta is going to be equal to the adjacent side divided by the opposite side, which means it's x divided by the square root of x squared plus a squared, the adjacent side divided by the hypotenuse of the thing. So if I put that in here, I'm going to get right out in front my lovely constants, q, 4 pi epsilon naught, and then cosine theta, which is going to be x, and then divided by x squared plus a squared, and the square root of x squared plus a squared, which for illumination here, I'm going to write as x squared plus a squared to the 1/2 power. Because what I have is in the denominator here an x squared plus a squared to the 2/2 power multiplied by an x squared plus a squared to the 1/2 power, and I know how that works out. So now I have my result that the electric field is equal to the charge over 4 pi epsilon naught x divided by x squared plus a squared, almost wrote that as cubed, x squared plus a squared to the 3/2 power, is my final result for the electric field at any position x along the x-axis. Now once again, well, I had said during this particular derivation that at the end I would want to evaluate it and see if that made sense. I've given myself a way to calculate what the magnitude of the electric field would be at any position along the x-axis. I might have some interest, by the way, in making a graph of that and seeing what it looks like. But here, I want to look at the extremum of the thing. Imagine that I take this position x along the x-axis where I'm investigating the field and I move it all the way into the center of the circular arc of charge. Now, it's difficult to see from my diagram, so in your mind, create your own diagram. Where I'm at a point that's at the center of the circular ring of charge. Every differential charge on the ring produces an electric field that points radially away. And so at the center of the ring, all of the electric field contributions will have an opposite member that will cancel out. My expectation, theoretically, in my reason, my ability to reason, is that the electric field should be 0 when x is equal to 0. Well, of course, my equation quite obviously bears that out. When x is equal to 0, I have an x in the numerator, so the whole thing goes to 0. So indeed, it behaves the way that it should. If I went through all of these machinations and got a result that didn't do that, I would have to give it a good rethink, but there you go. I also want to consider what happens if I go infinitely far away. Well, it so happens that you work this thing out. If I go infinitely far away, the limit of that thing is going to be 1 over r squared, or 1 over x squared in this case, because of the x-axis. Because if I go infinitely far away from the thing, it should behave like a point particle in observation. Now this result, it's like I'm doing these independent examples. This result not so independent. I'm going to take this result and put it aside and keep, I'm actually going to write it over here because I'll have to erase the board. I'm going to keep this result on the side because I'm going to use it as part of the strategy of solving my next example as it happens, my final calculus example for this particular session. And the technique that I'm going to use is probably going to be familiar to you from your studies of calculus, but it'll be in this physics context, and it's always good to see those things in two different ways from two different points of view because it improves and broadens our understanding and skill of the subject. My final example of this session is easily the most complicated, but it has, at this point, this is sort of building as we go with these arguments, it has some familiar elements, and in particular this diagram is going to look very much like the diagram of the previous example. It looks as though I'm going to draw a ring of charge again from that sort of three-dimensional perspective that I need to get the geometry of things, except this is not a ring of charge. It is a disk of charge. I'm going to assume that the distribution of the charge is uniform. That is, the charge density is the same everywhere where you examine this disk. I'll say that the disk has an outer radius r, so it's a circular disk, of radius, I'll call that radius capital R here on my diagram. Very tricky diagram to draw. And so once again, I'm going to ask the question, what is the electric field at some position along the x-axis? Because I know that I can get a satisfactory answer to that question. So it's a disk of charge, total charge positive Q, and I would like to determine the electric field along the x-axis. Here's my issue. I know what the procedure is. I need to divide this disk up into differential charges, find that differential of electric field, and add up all of those differentials of electric field. It would be extraordinarily challenging for me to say, well, let me divide this disk up into little circles of charge or squares of charge in the Cartesian plane. I'd find it very difficult to write the expression for the differential of electric field produced by a particulate element of this charged disk. So instead, I'm going to do something rather clever. I'm going to say, imagine that this disk is composed of, and it's very challenging to draw, but a set of concentric rings. The reason why I choose that strategy is that I have already computed the electric field created by a ring of charge. And so if I divide the disk into an infinite number of infinitesimal rings, then I'll be able to evaluate the total electric field by adding up those differential contributions. Once again, I'm going to imagine that the radius of the ring is A, but I've got a little bit of trouble. I'm going to have to be able, well, let's see what happens. I know, and I'll demonstrate the trouble as I go along. Once again, I'm going to say that the total electric field is equal to the integral of the differential electric field. And I know that there's going to be some angular issues and whatnot, but I already know the electric field due to a ring. So how do I write the differential electric field of a ring? Well, the differential electric field of the ring, what do we call this? dE I don't know, ring, the differential electric field of a ring. I don't like having a large subscript like that, but we'll go with it. The differential electric field of a ring is going to be the electric field due to any ring, simply, and the ring that I have my result that I left over here, I'm simply going to write the electric field due to a ring, but instead of the total charge Q, I'm going to write it again with the differential of charge. Because the only thing different between a differential ring and the, I guess, physical ring is that it has a differential charge. X divided by x squared plus a squared now to the 3/2 power. I might be getting a little, the audience might be getting a little bit nervous. I'm going to end up with this thing inside of an integral, and I'm going to have to integrate it. It's going to get worse before it gets better. But we'll take all of our steps carefully, and it's my ambition here to show every step, so it's quite clear. So I've written the differential of charge dq here in the numerator, and I'm going to perform an integral. Now, I have to be clear, and I've already had to do so once. I want to be clear, what is the variable? Well, as I'm performing the integration, again, mental animation. As I'm performing the integration, I'm going to be taking this ring and making it larger and larger and larger and larger and larger and larger and larger. And so the variable in this problem is the radius of the ring. The radius of the disk itself is a radius capital R, and that is a constant. As I perform the integration, it is the radius of the rings that will change. So A is the variable of integration. So when I seek to write this integral, where the total electric field will be equal to the integral of the differential of electric field produced by the ring, then I'm going to be taking the integral of, once again, bringing the constants out in front, and the only constants I have at this point are 1 over 4 pi epsilon naught, the integral of x dq over x squared plus a squared to the 3/2 power. I need a relationship between dq, the differential of charge of the ring, and the radius of the ring itself. So the question becomes, if there's a ring that has a radius A and a differential thickness dA, how much charge fits inside? Well, certainly a differential charge, but I'd like to find the relationship. So I introduced something a little bit new here. Instead of using the linear charge density, I'm going to use the surface charge density sigma. I'm going to say that my charge distribution has a certain charge Q, total charge Q, that is distributed over the circular area of the entire distribution. That is pi r squared, is the area of the distribution. The Greek letter sigma is generally used, not just in electricity and magnetism, but sort of all over the place, for surface densities. Beware, it has other uses in our physics as well. But for the moment, sigma is the surface charge density, the charge per unit area, which in this problem is going to be defined as the total charge Q divided by the total area of the distribution. But that is related, so sigma is equal to the differential of charge dq in the differential of area. Notice I'm using a capital A here. The differential of area of the ring. Now, there are really two ways of looking at the differential of area, and when we learn about it in calculus, because this physics problem certainly is brushing right up against counterparts that appear in calculus textbooks. When we study this in calculus, there are really two ways that we approach it. And I want to present both because I think it's worthwhile for us to encounter them. The way that I have in the past thought of answering the question, what is the differential of area, is that if I look at this ring here, this is the way that I was taught. It's a much more, it'll be appealing to the visual learners. If I look at this ring, and I imagine that it's somewhat flexible, and I can grab hold of it here and break it and stretch it out into a straight rectangular region. Here it is. I've taken that ring, I've pulled it off, and I've snapped it and stretched it out like this. I know that the length of that ring is the circumference of the ring, which is 2 pi a, the circumference of the ring. And I know that its thickness is the differential of the variable lowercase a. The lowercase a is the radius of the ring. You've probably caught on now to the fact that I'm using a because I've got the r that appears as 1 over r squared in physical laws. I've got the capital R that is the r of the distribution, so I've run out of r's, which is why I wisely chose to make the radius of the ring lowercase a. So if I were to write the differential of area of this ring, now cut and stretched out, then that differential of area would be the length times the width. It would be 2 pi a dA. And that's a perfectly adequate way to coming to the conclusion that the differential of area is equal to that. Another way of looking at it is to appreciate that if the area of a circle, or if the area of if the area of a circle is pi times a squared, I lost my mind for a second, then the differential of the area of the circle dA, so dA, you don't get to write that very often, dA would be 2 pi a, and so the differential of area would be equal to 2 pi a times dA. And so I get the same result. One way is looking at it with a little bit of imagination, you might say a visual way of evaluating the differential of area, and the other way is sort of a calculus way by using the derivative. Either way, now my surface charge density sigma, which is dq over dA, becomes dq divided by 2 pi a dA. And now I can solve for, pardon me, I wrote that as an uppercase a and I meant a lowercase a. I have to be very careful. And it happens, just a little bit of foreshadowing, it happens that in the future of our physics, being careful about which variable is which is going to be really important, because this having multiple radii and multiple geometric things to describe is never going to go away. So we have to be very careful with the symbols. So solving this around for dq, I find that the differential of charge that is found inside a differential ring of radius a is going to be equal to, I'm going to arrange these in what I think is a pleasing way, 2 pi sigma a dA. The reason why that pleases me is that I've got constants, and then I've got variable, and then I've got differential. It's a sensible thing. So now I'm going to make that replacement in my integral here, and just to make things continue to look lovely, I'm going to take all constants in front of the integral, and just for your educational purposes, I'm not immediately going to do any kind of cancellation. So I'm going to write that this is 2 pi sigma, which are my constants from dq, 2 pi sigma, over 4 pi epsilon naught. Again, not making the cancellations yet. I will, probably in the next step. The integral of x a dA divided by x squared plus a squared to the 3/2 power. So now, I've done all of the setup. It was significantly challenging because I'm not using the point particle setup, so I had to use the differential of ring. And I had this new surface density thing to describe and manage, but now I've got it down to an integral that I can solve. And you may say, some integral. By the way, I'm looking at it right now. I have the x in the numerator, x a dA. X is also a constant because I'm looking for the electric field at a particular x. Once again, when I get my answer, I may move x back and forth and consider what happens. But that x is a constant. And so I'm going to amend my equation right here. And instead of having x a dA in the numerator, I'm going to move that x outside the integration and put it out front there. I have a feeling at the end of the integration, I end up moving it back in again anyway. But I just want pure calculus on the inside. Warning, we do so much calculus where x is the variable. X is not the variable here. A is. X is not the variable, A is. So we have to sort of change our calculus thinking. But if we're very practiced and skilled at it, we should be able to make that transition without any trouble. Now, before I begin to do the integral, which is going to involve some u substitution and some more, new techniques, things we've learned recently. I want to consider limits of integration. To consider the entire charge of the disk, I'm going to need to begin at the origin of my coordinate system and integrate outward so that the limits on the integration of the variable a, which is the radius of the rings, is from 0 to a. So there's my integral, and I need to solve it. Well, it's a little bit of a troubling integral when you first blush take a look at it, because you say, well, look, I've got an a in the numerator and I've got an a in the a squared, it's in the denominator, and I don't immediately have like a rule of calculus. I can't use, it's not, like integrating a polynomial is quite simple. This is more challenging. So what we'll do is we'll avail ourselves of some clever U substitution. And here the clever choice, and I'll explain why in moments. The clever choice for U is x squared plus a squared. And immediately what I do when I perform a U substitution is take the derivative. So the derivative of U with respect to a is going to be equal to 2 times a. And so I'll be replacing not dq, I'll be replacing dA in my integral with du divided by 2a, and you immediately see the advantage. When I make this substitution into the integral, the a that appears in the denominator of my substitution for dA will cancel the lone a in the numerator, and I'll be left with an expression that is entirely in terms of u. Let's write it out in its u form and take a pause from the limits of integration for just a second. 2 pi sigma x over 4 pi epsilon naught. Those are my constants, but I get another factor of 2 that comes out, because when I make the substitution that dA is du over 2, that 2 comes out as well. And I still haven't done the cancels. You know what, let me do the cancellations here. I don't think it'll hurt anybody's feelings. When I make the replacement, dA with du over 2a, there are 2 cancellations that happen. First of all, the factor of 2 that appears in the constants out in front can cancel away. And, by the way, there's a pi in the constants out in front that I never bothered to cancel. And so what I'm left with outside is sigma x over 4 epsilon naught, the integral, and now I've made my u substitution. So my integral is du divided by u to the 3/2. And so now, by a careful choice of u, which is the whole trick of doing u substitution, I've taken an integral that I could not do on its face and replaced it for one that I can. Now, these integrations of monomials, yes, the strategy is this. You promote the exponent and then divide by the promoted exponent. If I look at my equation sheet for integration, I'll discover that it's there. I promote the exponent and divide by the promoted exponent. Well, here, u to the 3/2 is in the denominator, so that's really u to the negative 3/2. So it's u to the negative 3/2, and I'll promote that, which is negative 3/2 plus 1. Well, negative 3/2 plus 1 is negative 3/2 plus 2/2, which is negative 1/2. And then divide by the promoted exponent, which is multiplying by negative 2. So the result of this integration, see, I know that was a lot just done in our heads there, but the result of this integration is going to be negative 2u to the negative 1/2. Well, of course, u is a contrivance. It's a thing that I invented to assist me in solving the integral. I don't want to leave that u in there. I want to replace it with what u is equal to. So here I have a factor of negative 2 that I'll take out in front again and cancel with the 4 in the denominator. You'll see that happen in just a moment. And I'm going to put u back in and replace my limits of integration. So my electric field will be, subject to limits of integration, negative sigma x over 2 epsilon naught. That's that 2 from the integral, canceling the 4 in the denominator. And then what do I have? X squared plus a squared to the negative 1/2 power, evaluated from 0 to a. So I'm going to go ahead and do that integration, and I'm going to end up with 2 terms. So you have to be careful. Subbing in 0 for this is not going to result, as it often does, and I'm always happy when it does, result in 1 term. That's not going to happen here. I have to evaluate both terms. So this thing evaluated at a is going to be 1 over the square root of x squared plus a squared. and evaluated at A is equal to 0 is going to be 1 over the square root of x squared. When A is equal to 0, it's 1 over the square root. It's 1 over the square root of x squared. Well, 1 over the square root of x squared is simply x, so it's 1 over x. I'm not wild about this negative sign that is hanging around outside of my result here, so I'll bring it inside the bracket, which is going to reverse the direction of the subtraction. I've set myself up for some additional writing here, but I have this skill where I can talk and write simultaneously, so I'm just reversing the order of the subtraction. 1 over x minus 1 over the square root of x squared plus a squared, and that would be my result, but I'm not 100% on it because I have an x outside the brackets, and just for style points, I'm going to multiply that x through the brackets and declare that my final result for the electric field along the x-axis due to a disk of charge q and radius capital R. I made a mistake. I made a terrible mistake. Nobody spoke up. My upper limit on the integration is not a, but in fact r, which means this is not a, but in fact r, which means when I reverse it, it's not a, but in fact r. So my final result, I didn't have it in terms of, boy, that's dreadful, is going to be sigma over 2 epsilon naught x. No. Now you see I've flustered myself because I chose the wrong limit. And I had to substitute capital R back in for the A, and that flustered me. And so now I have to, so I'm going to multiply through by x, just as I was saying before I realized my error, is 1 minus 1 over the square root of x squared plus r squared. That is, I think I misspoke as I said that. So the final electric field is sigma over 2 epsilon naught, the quantity 1 minus x over the square root of x squared plus r squared, which is the most sophisticated integral that I think probably we might claim the most sophisticated integral that we've done in our course so far. Well, you can see that even when I make requirements of very careful and useful symmetries in the problems and limit the problems to finding the electric field at specific points in space, the mathematics becomes challenging very quickly. If I were to look for the electric field anywhere off axis or in arbitrary locations, and then also when I make the distribution of charge in space non-uniform, the mathematics of it can become very sophisticated. There comes a point now in our modern age, and I wonder if some of our friends in the room who are avid computer programmers consider that they might create some sort of numerical recipe for computing the electric field everywhere in the vicinity. Well, of course, this has been done, and one can even buy a package of software where you show it, you sort of, as the input to the thing, you say, well, this is my distribution of charge in space, calculate for me the electric field everywhere. I think that's quite spectacular that we've reached, because that technology did not exist when I was a student, or at least it wasn't commercially available, and we were only beginning to solve problems of physics using computers. But I love it that now I can do that and I can visualize electric fields, but I suggest caution. It's very important that I have this fundamental idea of the behavior, that I kick it around a bit, that I mess with it and see what it does, so that when I ask some computer program to solve the problem, that I can have some intuition about the answers, which could potentially spare us all from a tragic mistake.